Lecture 33, The Brittle Regime. The brittle regime is where the physical conditions promote brittle deformation at the grain scale, such as frictional sliding, grain rotation, and grain fracture. And at the mesoscopic scale, such as fractures and deformation bands. The brittle deformation mechanisms at the grain scale are granular flow and cataclastic flow. Granular flow involves frictional sliding and rotation of the grains. It is common during shallow deformation of porous rocks. Cataclastic flow involves in addition fracturing of the grains into smaller fragments. It occurs at higher depths, during deformation of well-consolidated, lower porosity rocks. At the mesoscopic scale, brittle deformation produces fractures and deformation bands. Low porosity rocks respond to stress in the brittle regime by forming extension and shear fractures. Such fractures are sharp and mechanically weak discontinuities that can be reactivated during renewed stress. In highly porous rocks, brittle deformation is expressed by related, although different, structures known as deformation bands. In the brittle regime, low porosity rocks can develop extension fractures, shear fractures, or stylolites. These are known as anticracks and are perpendicular to the shortening direction. The corresponding structures in highly porous rocks are dilation bands, shear bands, and compaction bands. For all these structures, the ratio of thickness to displacement is given. Fractures are very narrow zones, often thought of as surfaces, associated with discontinuities in displacement and mechanical properties of the rock. Fractures can be classified into four modes: Mode 1 or opening fractures, Mode 2 or sliding fractures, Mode 3 or tearing fractures, and Mode 4 or closing fractures. This is a low porosity rock sample under sigma 1 vertical, and sigma 2 and 3 horizontal. Mode 1 fractures or joints form parallel to sigma 1 and perpendicular to sigma 3. Mode 2 fractures or shear fractures form as conjugates at an angle phi, often 30 degrees, from sigma 1, and their intersection is parallel to sigma 2. Mode 4 fractures or stylolites form perpendicular to sigma 1. These are the structures that develop during extension and contraction of low porosity rocks. Elastic deformation is observed initially for all cases, while ductility increases with temperature and confining pressure. In the stress-strain curves, Yp is the yield point. Extensional fractures form at low confining pressures in the brittle regime. Shear fractures form in the brittle regime. Shear bands develop in the brittle ductile regime. And in the ductile regime, the deformation is more distributed, and strain increases at constant differential stress. This is known as plastic flow. Deformation bands are millimeter-thick zones of localized compaction, shear and/or dilation in porous rocks. They are thicker and show smaller displacements than slip surfaces. They maintain or even increase rock cohesion. They are low porosity and low permeability in relation to the host rock. They contribute to strain hardening in contrast to the softening associated with fractures. And they occur in zones associated with slip surfaces. Deformation bands can be classified with respect to the relative movement of the sidewalls. Simple shear bands are characterized by displacement exclusively parallel to the band. Compaction and dilation shear bands involve both shear and displacement perpendicular to the band. Compaction and dilation bands are characterized by displacement exclusively perpendicular to the band. Deformation bands can be also classified according to the deformation mechanisms involved in their nucleation and growth. Disaggregation bands accommodate shear primarily by sliding and rotation of mineral grains. Little or no cataclasis is involved. Phyllosilicate bands form in sands containing more than 15% phyllosilicates. During shear, the platyphyllosilicate grains rotate to align with the band. Cataclastic deformation bands form narrow millimeter-wide zones of crushed grains. In the center of the band, the porosity and permeability are nearly zero. Cementation of the bands can occur at depth greater than 2 to 3 kilometers. Disaggregation bands are almost invisible in outcrop, and their presence is manifested by offset of sedimentary lamination. Cataclastic bands are harder and they stick out. Phyllosilicate bands are darker due to the alignment of mica minerals along the band. These are compaction bands formed perpendicular to sigma-1, which overprint less noticeable disaggregation bands. This is a cataclastic deformation band in a sample, and a thin section, of a sandstone. The band is about 1 mm thick. Pore space is colored blue in the thin section. It is clear that both porosity and permeability are drastically reduced in the band. The left photo shows a meter-thick, dense cluster of cataclastic deformation bands. These clusters often occur along slip zones. The photo to the right shows a conjugate array of cataclastic deformation bands in poorly consolidated sediments. The bands have a positive relief since they are harder than the host rock. Textural and mechanical properties of the host rock, in addition to burial depth and confining pressure, are key controls on deformation bands. Disaggregation bands form at shallow depths in unconsolidated sediments. Phyllosilicate bands form in sediments with more than 10 or 20% phyllosilicates. Cataclastic bands form preferentially at 2 to 3 km depth in well-consolidated sediments. Extension fractures are most likely to form during uplift and erosion. To learn more about this topic, please read Chapter 7 of Fossen, and do his e-learning module on brittle deformation. And answer these questions.